hits the front of the range and sublimates, whereas the meteorites are left behind. So there are concentration zones all along the front of the mountain range, and that's where our expeditions go to recover samples. So I thought it would be good to show you the context for our collection before we head into the lab. This is just a big picture kind of overview, but if you have some questions later about the field aspects, let me know. What we're going to see today are the curation activities that we oversee here at JSC. So with that, we'll head into the lab. All right, come on in. We're going to first put booties on over our shoes before we go into the lab where we put the gowns on. And let's see here. So we're going in a class 10,000 or an ISO 7 rated clean room. And that's a little bit cleaner than where they put together a spacecraft for various space missions, but slightly less clean than, say, the Stardust or Genesis labs, which are also in our astromaterials curation collections. But we'll go in, we'll put on a gown and a cap, and then we'll head into the lab. We'll go through the air shower and head into the lab. We'll go in there. All right, after you. Thank you. Thank you. All right, now let's see. I was just in the lab making sure we had some samples out. So my gown's already out here. Very simple, just snaps on the front here. And, oops, oh yeah. And then I put just a simple cap on here as well. And make sure that doesn't get my ear. And all right, so I'm set. I can hold for you, Suzanne. So while we're getting ready here, I'll just show quickly here. This is the air shower we'll go into, and this air shower leads into both the meteorite lab, which is the door there on the right. You can see, we'll go through that one. But straight ahead and sharing an air shower with us is the cosmic dust lab, and the cosmic dust collection consists of particles that are collected with a high altitude plane with collectors under the wings. They collect particles from the stratosphere, and they're returned here on a regular basis and stored here in the Cosmic Dust Lab, and those are available for researchers as well. So these are the two collections that are sort of Earth-based. They're astromaterials that are collected on Earth. So we that's sort of distinctive, fundamental difference between the other collections, which are from missions, NASA missions. Here, I'll pass this back to Suzanne. She's all ready.
While you're getting ready, and you mentioned how this is a clean room, can you tell us why do these labs need to be so clean?
The clean room environment was established for this collection because we want to minimize the additional potential for contamination of the meteorite samples. And so what I mean is, for example, if we just stored them in a regular room, like a large office space, there would be dust and dirt from the hallways that would get in. People would bring in some dirt from their clothing, and none of it would be monitored potentially. And so there would be a lot of uncertainty how much contamination the samples experienced. In a clean room environment like this, we have the ability to control the airflow, the air quality, the particulate matter in the air. It's cleaned regularly. There are only a short list of approved materials that are allowed to be in contact with samples and or be in the clean room environment. And so it just helps to protect the samples for the long-term preservation for the science community. So that's the reason. All of our collections are in clean rooms, and the clean rooms are sort of customized to fit the needs of the collection and in a very practical way. So I hope that helps. But let me know if you have questions about that. One of the ways we keep the clean room clean is to use the air shower, which removes loose particles from people before they enter into the lab. And so we'll do that now. We'll open up the door here and step up in. And I will also remove my ring. So we don't want samples to be touched by any precious metals like gold or silver, platinum, because they can potentially contaminate samples as well. So here we go. You'll hear the fan for about 30 seconds in the air shower. All right, as soon as this ends, we'll step out. We'll open the door here and step out, and watch her step down there. And we'll enter. So we've just entered into the Antarctic Meteorite Lab, or processing lab. So this is about 5 small rooms that are all connected together that help we've got capabilities in each room that help us curate this collection. And so what I wanted to say a little bit before we look at samples is, so I tried to spend a little time on the map out in the hallway showing where the samples come from. And our collection is kind of unique as far as the collections here go, the collections here at JSC, because it's managed by 3 different institutions. So we already know about NASA, and we have the National Science Foundation that helps us with the field expeditions that are run out of McMurdo Station. And NSF, the National Science Foundation, they oversee that operation and provide support for our field teams to get out and collect samples on an annual basis, with the exception of the last couple of years because of the pandemic, which has sort of stopped research groups like ours from carrying out research down there, or carrying out the expeditions. But the NSF works together with us and the Smithsonian Institution. The Smithsonian Institution has 2 roles. They help us with classifying the meteorites. And when the program started in the mid-70s, they had a lot of meteorite expertise at the Smithsonian. The Smithsonian is the long-term home for the collection. Ultimately, all meteorite samples that are U.S. government property should eventually end up at the Smithsonian. And so they're also a long-term storage facility for the meteorite collection. The role that we play here is we receive the samples as they come back from Antarctica. We do the initial characterization. We announce the availability of the new samples in our newsletter, which is twice a year. And then we keep what we call the active research collection here at JSC. so that our staff can help to prepare and allocate or ship out to scientists the samples that they've been approved to study. So it's a very everyone has a very well-defined role. We've been doing this, as I mentioned, for about 45 years, since 1978, and coming up on 45 years. And we are very busy, as the collection efforts have brought a total of 23,000 meteorites back from all the different collection seasons. So it's a large collection, and in fact, it has become too large for our facility here. And maybe about 20 or 25 years ago, we started sending small quantities of samples that are not studied as frequently to the Smithsonian for long-term storage. And that's enabled us to free up space here for new samples that come back with the new expeditions. So that's a little background. As I said, the involvement of the three agencies makes our collection unique, different from the other collections here, which are just managed and operated by NASA. So we have our own set of constraints that we have to work with, working with a larger group and across agencies. So I wanted to say a little bit now about the process. And so we, as I mentioned, the samples come here first. When they're collected in Antarctica, they're frozen. We put them in boxes or isopods that allow them to stay cold while they're being collected out in the field. When they return to McMurdo Station, they're put in the science lab there into freezers, so they're kept cold during the temporary storage there. When they leave McMurdo, they're put on a cargo ship. The cargo ship goes from McMurdo to Southern California, Port Hueneme. While they're on the ship, they remain frozen. They're frozen at Port Hueneme for short-term storage, and then they're shipped across from California to Texas in a freezer truck. And they arrive here frozen, all the way frozen since they're at the point at which they were collected by our teams. So when they get here, what do you think we do? We put them in freezers too. Here's another freezer. Here's some meteorites. Let me open this door here. We'll only open these for a couple seconds, but these meteorites are all bagged and frozen, and they're waiting to be characterized by our group here. And here I'll close that real quick. So they're probably, at any given time, we have anywhere from a few hundred to 1,000 meteorites that we have in temporary storage here, waiting to be characterized. So if we let's go back out here. Now, we keep them frozen. Meteorites, they contain iron, nickel, metal, and they contain some other minerals that are stable only up to certain temperatures, a few hundred degrees. And so one reason we keep them frozen is because we want to minimize any kind of oxidation or transformation, mineralogic transformation that would occur if we just put them at room temperature in there and let them thaw in their bags. That's dangerous or risky because we've got humidity in the air, and we've got temperature, room temperature may be a bad combination with the humidity for alteration and rusting and so forth. So what we do instead is we thaw them out in controlled nitrogen atmosphere here. You can see a few meteorites in this cabinet here. We remove them in small quantities from the freezer, maybe 10 to 20 samples at a time. we put them in the glove box here with nitrogen flowing, with the bags cut open, so any water or ice or snow that was collected with the sample has a chance to be removed. And we do this before we work on them out in the lab or in other cabinets. So this is an essential first step. We call this the thawing cabinet. And every sample goes through this cabinet before we work on it. That way, so sometimes we'll have groups of 50 in here. Larger samples may have to go thaw for a day or two, so that we're certain they're totally thawed. And once they're thawed, though, then we start to characterize them. And so we do that on a flow bench. And there's an example of a flow bench here. The flow bench is a kind of a broad, flexible space that we can use to do basic things like photography. We weigh the samples. We'll make some initial observations about the sample, about its color, its textures, how much metal might be present, how much fusion crust. So meteorites, when they come through the atmosphere, they heat up, and the outer portion of the meteorite starts to melt, and it forms a thin molten layer that quenches to a glass by the time it makes it all the way through the atmosphere. And so sometimes samples will be completely fusion crusted, and we won't know what's inside them till we break them open. Other times they'll be the fusion crust will be crumbled away, and we can see already what kind of meteorite it might be. So we get these meteorites in various physical conditions. Sometimes they're very difficult to break. They're very coherent. Other times they're altered. They're crumbly or fragile, and we have to be careful how we handle them. So there's a really broad range of conditions at which we receive samples here. Anyway, this is all done here. We'll do the characterization at the macroscopic level. And then I mentioned earlier the Smithsonian is involved. And usually we'll either make a thin section, which is a very thin 30 micron thick slice of a rock or a meteorite that's epoxied to a glass slide. And then we can use that then on a microscope to determine the detailed mineralogy, and we can put it in other instruments to determine mineral composition, mineral textures, and zoning and things like that in the chemical zoning in the minerals. And so all of that information helps us classify the meteorites. The other way we do classification is a more rapid approach where we mount maybe 40 or 50 samples at a time in a little plug, and we can look at the composition of the minerals in each of those little sample holes in the epoxy plug and classify together with using macroscopic observations. We can classify large numbers of samples at a time. And the reason we do that is because most large meteorite collections like this, they have somewhere between 80 and 85% what we call ordinary chondrites. And ordinary chondrites they have that name maybe for obvious reasons. They are the most ordinary samples. If you find a meteorite, it's most likely it's going to be an ordinary chondrite. There are three kinds. There are L, LL, and H chondrites, and each of them, L and H, make up probably about 70% of all meteorites, and then the LL make up about 10%, something like that. So because they're so common, we want to classify them as quickly as we can, because it's really the other 20% of the collection that we're most interested in. And so that other 20% will make thin sections and spend more time documenting their unique features, which may be of more interest to the science community. So anyway, that's all part of this initial processing that we do, characterization of the new samples. Twice a year, we compile all that information into what we call the Antarctic Meteorite Newsletter, which is released to the science community. And at that point, people have a few weeks to put in a request for new meteorite samples that they may have read our description and said, hey, that sounds really interesting. That's the kind of sample I've been waiting for. We get requests maybe about anywhere from 80 to 100 a year. From 80 to 100 different scientists. And then we have committees that help to evaluate those requests and say, yes, we recommend that this request is approved, or I'm not so sure about this request. You might want to deny it and ask them to provide more information, something like that. We get recommendations from our committees. We put that all together, and twice a year then we have this cycle where we prepare samples. Once they're approved by at the headquarters level, we prepare samples and send them out to the science community. So this is a busy lab. We have these 2 cycles a year. We have new samples coming in usually every year. And we have to identify samples that we want to remove from the collection here and send to the Smithsonian for longer term storage. So those 3 kinds of activities really keep us busy and allow us to make new discoveries with the new samples that are coming in. So I've talked a little bit about the initial processing part. When we start doing preparing samples for allocation or sending to scientists, we have some facilities for that too. So right here on my right here is the Mars meteorite cabinet. So this cabinet is dedicated to only Martian meteorites. If we introduce a sample into this cabinet, we do processing, and then we remove the samples. It will get cleaned before we do processing of another sample. And in another room, which we won't go in there, but we have a cabinet just like this one, which is dedicated to carbonaceous chondrites. And it's for the same reason. We want to have a clean, very highly cleaned and controlled environment in which we can process carbonaceous chondrites and Martian meteorites, because they contain, or they might contain, organic compounds that we want to keep as pristine as possible. We want to minimize contamination from humans and from the environment. And so we do the processing in these cabinets. So those are our 2 most extreme kind of processing environments. We do have a few other cabinets like this one. We can use, we can clean this out and use it for a sample type or a sample of interest. In the past, we've had lunar meteorites that we've decided to process all at once in this cabinet because there were so many allocations that had to be prepared, and so it made sense to do it in there. But we also have flow benches. We have 3 flow benches like this one that we use for all other sample preparation. And so the flow bench, the flow bench environment is clean for, it's a clean environment for meteorites, and it still allows our processors the dexterity and flexibility to work on large samples and large numbers of samples too. So we have a lot of samples to work on with the facilities that you see here. So we need to be able to process samples a little bit faster than the other labs because of that. So let's see, just a couple of other quick things. Maybe we can go this way. We have some storage, different kinds of storage medium. We have these large volume cabinets where we can put large meteorites. Against the far wall there, you see smaller trays of meteorites, and we can go back. Yeah, we can go back here. These are each of these trays here contains small splits of meteorites, and I won't open them up, but we can look at some others in the other room. But we have a number of different ways we store meteorites depending on what's practical and what's easy for our staff to access. And we have a lot more of these storage cabinets back here. And then here are some typical meteorite splits that are in vials. They can be in either glass or plastic vials or in bags like these on this side. And these are easier to show you. I thought these might be better to pull out for the tour. But you can see we have many splits. We have thousands of samples here, and they're all tracked in our database, so we know exactly where each one is. So let's go back. I wanted to show you a few other facilities in the back room, and then we'll look at some samples too after that. But we'll come back this way. We'll go through this. Watch your step here, up and then back down. So this is another one of our rooms for the collection, and I like to show this cabinet here. This is a unique kind of cabinet we have. It's a bandsaw cabinet, and there's one almost identical to this one up in the Apollo lab as well. Many rocks have been cut here. I think we've cut probably about 120 or 130 meteorites at one time or another in this cabinet. It's an interesting design. There's a foot pedal that you can control to turn the blade, the bandsaw blade on and off, and then you physically push the sample through when it's sitting on a tray, and you can make a nice cut. So we don't do this with every sample, because what happens is when you start cutting a sample, there's sawdust that goes everywhere, or rock dust, and it coats the windows and the floor and the sides of the cabinet. So after every cut, every rock that's cut, it needs to be cleaned out to prevent contamination. So, which is very labor intensive. So we only cut samples here when we really need to, and that's when we have, for example, a special rare meteorite that's also large enough to cut, and we have had many requests. One example would be in the 2004, we had a Martian meteorite, a knocklite from the Miller Range that we cut here because we had 50 requests, 50 different requests at one meeting for that sample. And so we realized that if we cut a slab of that knocklite, about a 1 centimeter thick slab, we could fill most of the requests from that one piece, and that left about 75% of the rock still untouched and close to pristine. So it made sense for preservation and for a practical approach to filling all those sample requests. So we'll do that. Another reason we'll cut a rock is to see the interior texture, and sometimes that's really difficult to see on a 1-inch round thin section that we typically use. So if we're able to cut through it and see what's in on the scale of 4 or 5 inches, it gets us the big picture or a bigger picture. So we'll do that occasionally. So this is one highlight of this room. The other highlight is is this sample here, which this sample is one of the ordinary chondrites that I mentioned. It's an H5, one of the most common meteorite types in world collections. But in our collection, it was found in 1985. It weighs 225 pounds, so it's very heavy, and it's obviously too big and too heavy to handle to put into one of our storage cabinets. So this is a customized cabinet or nitrogen box that was built to house it in the mid 80s, and so it's conveniently on a cart too. So we can disconnect the nitrogen flow and move it around. It's a sample that because it's not scientifically, it's not a rare type and it's not in demand scientifically. It's been studied just a little bit, and you can't really see evidence of the sampling, but if you were to tilt it up on its end and look at the bottom, you'd see a couple of drill holes where drill cores were taken for the initial characterization. And that's really the only place it's been sampled aside from points on its exterior where you see these white crystals. These white crystals that are around the exterior are terrestrial weathering products, sulfates, carbonates, and oxides, several other minerals that formed as the meteorite sat in the ice in Antarctica. And so some of the most detailed studies or extensive studies requests that we've gotten for this sample, which we call Big Lou, are from scientists who study the weathering products. So we like to have it in our lab. It's one of the few samples that is not in a bag, so it's easier to see. You can see all these exterior features. It's big enough that everyone can look at it at once. You don't have to pass it around and look one at a time. And it also gives an opportunity to talk a little bit about the potential or the threat of near-Earth asteroids hitting Earth. And so these are the most common, H5, H chondrites are one of the most common types of materials that fall to the Earth. And sometimes they fall in showers or strewn fields, which means the sample broke up in the atmosphere and then showered down to the ice. And those events occur occasionally. For example, there was one in Russia. They can occur in populated areas. There was one that fell in Russia in 2013 called Chelyabinsk. You may have, I don't know if you remember hearing about that or not. It was an ordinary chondrite. And since then, there have been a few others that have fallen too. But we have a number of these large strewn fields or pairing groups of ordinary chondrites in our collection. And there's always a good possibility that somebody will come in and do a detailed study of some of those large impact events like that that may have brought a lot of material to the Earth. So they're preserved in the ice and available for study. So I always keep that in the back of my mind. We get a lot of interest in non-ordinary chondrites, but really these are potentially really interesting as well to help us understand hazards, impact hazards. So we have a couple of samples we wanted to look at real quick in the other room. And if you, let's head back out, watch your step again there. And let's see. I've got a few samples on the flow bench here. I'm going to put some gloves on before I pick them up. So we have a couple of samples here. I wanted to show this is actually a carbonaceous chondrite. It's a CV chondrite, classified as a CV chondrite. As you can see, I'll turn it sideways here. It's a 1 centimeter thick slice of a larger meteorite. It was originally probably 3 or 4 kilograms. We cut through the middle to generate this slice. And I'm not sure if we can see. Yeah. Oh, great. So there are some white inclusions or large features that are light colored in this sample. You can see in the cross section. And I like showing this because these are calcium aluminum rich inclusions that are made of minerals like melilite and anorthite, vanille, ackermanite, galenite. These minerals all condensed from the solar nebula and at high temperatures, and they are some of the oldest solids that are known in all materials, all astromaterials. So these are found in CV chondrites. In fact, there are a couple of circular holes in this sample, and they were probably CAIs, or those calcium aluminum inclusions that were drilled out to be studied by scientists. So I like showing this sample. You can see these macro features pretty easily. And then also, there's been a lot of interest recently, and it'll continue for many years, in carbonaceous chondrites and carbonaceous asteroids like Bennu and Ryugu, which are the target asteroids for the 2 missions, OSIRIS-REx and Hayabusa 2. So I have another carbonaceous chondrite slice that I got here. So like the sample that you just saw, which has the really evidence for really old materials locked into it. This one is a carbonaceous chondrite, but it's a CR chondrite, and it has some aqueous alteration. In other words, water has moved through this sample, probably on the asteroid parent body, and altered the minerals that were there by reaction with the water. So there are minerals like phyllosilicates and other hydrated minerals that are contained in this sample. So these 2 kinds of meteorites are carbonaceous. Like I said, they make up about 50% of the asteroid belt. And with those 2 missions, we're about to learn a lot more about carbonaceous asteroids in the next 5 or 6 years. So stay tuned. I got these out really to emphasize that current interest in NASA and JAXA. And then the other sample I have out here is one. So we talk about the Martian meteorites, and I showed you the Mars cabinet a few minutes ago. Well, that just happened. I just said that so easily and effortlessly, but you might be thinking, oh yeah, sure. How do you know that's from Mars? How do they know these meteorites are from Mars? Well, this particular sample was one of the meteorites that allowed that connection to be made. This is it's a basaltic rock. That's weird enough to have a meteorite that's a basalt. That's very rare. But this particular basalt has these black glassy pods that you can see, and also more difficult to see, but they're melt veins that cut across the sample as well. If we could look through the bag and see a little more detail, but these glassy pods are thought to have formed upon impact when a meteorite is released from its parent body from an impact. That particular impact is high enough pressure and temperature that some portion of the sample will melt instantaneously or within a fraction of a second. And when that happens, those little melt pockets are preserved in the rock, and some of those rocks make their way to the Earth. So in this particular sample, these black glassy pods were analyzed for their noble gases, argon, krypton, xenon, helium, in the early 1980s. And the scientists were puzzling over the noble gas signature. It was very different from any meteorite that they had measured. And after some time sifting through geochemical data that we had assembled, they realized that the noble gas composition was identical to the noble gas composition that the Viking mission had measured. The Viking spacecraft lander had measured on the surface of Mars in 1976. When they realized this was the biggest piece of evidence that links meteorites to Mars, and it still remains to this day, 40 years later, really good, the best evidence for a link between meteorites and Mars. So there are other features that we recognize now that are distinct and give us a hint of the Martian connection, like the bulk composition. Mars tends to be more iron-rich. There's some other isotopic compositions like oxygen that are distinct for Mars and for other planets and asteroids. But really, the noble gas signature is the main connection that's made. And so whenever we get a meteorite we think is Martian, somebody measures the noble gases to make sure they look like the Viking mission. So I like showing this sample. It was a really large, I think it was an 8-kilogram sample originally. It's a ton of material. It's allowed people all over the world to study pieces of Mars for one reason or another, for a whole broad range of scientific disciplines. And we still have so much of it left for future studies. So anyway, I like explaining a little bit about the connection to Mars. Our collection is really diverse. We have samples from probably literally hundreds of different parent bodies. Not all of them have been identified, but we also have samples from the moon, for example, and lots of asteroids. So I get the feeling I've talked enough, and I want to leave some time for questions. I'm happy to answer questions you might have.
So this individual is wondering, does the absence of face masks indicate that you're worried more about geological contamination or microbial contamination, or can you talk a little bit about that?
Yeah, I can say a few things about that. So we don't wear face masks. We haven't. We could. If we were, so part of the reason for the meteorite, there's a little bit of extra flexibility for the meteorite lab because the samples have typically, and I hadn't mentioned this before, but typically they've sat either on the Earth's surface or in the ice for hundreds of thousands of years. So they've been exposed already to microbial systems, I guess you would say, or terrestrial systems, both in the ice. During their collection by the field team, people are bundled up to stay warm, but there's no, there's no precaution taken, especially as they're being collected, other than people use tongs to pick them up, and we clean the tongs and send them out to the field team before every season. We have bags that are used, Teflon bags for the collection and Teflon tape, so the samples aren't handled in the field directly, unless it was, just an accidental touching or something like that, but that's very rare. And then once they're in this environment, we keep them, as I mentioned, in these controlled conditions and areas, and they're stored in a clean environment. That's really just to keep the extra contamination to a minimum, and so that we've found that's adequate for storing meteorites. And in this this particular environment or collection, we're probably the most extreme or the cleanest environment of any meteorite collection in the world. So we have a lot of curators who visit us, and they're excited because everything is clean and shiny in here. And so every time, we feel really happy about that. But we do think about it every once in a while, is this overkill? Are we doing too much? But really, I don't think so. I think it's good to have a long-term plan like this that accounts for minimizing contamination potential. So hopefully those additional comments help answer that question.
How can we, as interns or perhaps future scientists, get involved in field research such as Antarctic meteorites?
Oh, yeah. For the Antarctic Meteorite Program in particular, it is a volunteer program, and it's not run by us. It's run by two scientists who are based at Case Western Reserve University and the University of Utah. So Ralph Harvey is at Case Western, and Jim Carner is at University of Utah, and they organize the field teams. They have a lot of people writing them letters or coming up to them, introducing themselves at meetings. I think at any given time, they probably have a long list of potential applicants who are ready to go, really excited about going. And that list is comprised of probably graduate student level people, postdoctoral scientists, faculty members. The year I went, which was 99-2000, that's before I worked at NASA, there was a retired faculty member from Case Western who went along. He was an astronomy professor, and anyway, it's a wide range of backgrounds of people who go. Not everyone is a meteorite scientist either. So they've had people go who are journalists or writers, teachers, or science teachers. And so anyway, I would encourage you, if you're interested, to contact Ralph Harvey or Jim Carner for our particular program. But fieldwork in general is tougher to make recommendations, because I think field studies of meteorites are carried out by so many different people. I would recommend looking in the literature about particular meteorite falls or recovery efforts and see who the authors are. Sometimes those people are at universities and they have funding to recover meteorites, or that's their specialty, and they're known internationally for that. But you could contact them and express your interest and ask how you can get involved. Sometimes that can work, and sometimes if you contact somebody at the right time, they might have an opportunity for you. So you never know. So I hope that helps. That's a little bit of advice. You have to be patient and wait for nature too, for the next meteorite event, or strewn field, or meteorite breakup event to go recover material. That's exciting too, but we never know when it's going to happen.
Now, for the ANSMET expeditions, Kevin, the first time you applied, were you accepted? And is that the norm, or do you sometimes have to apply numerous times before you're accepted?
Yeah, I think I wrote my first letter in 1996, and then I either reminded them, at that time it was just Ralph Harvey. I either reminded Ralph at a meeting, or I sent the letter to him again. And then, so I had to wait about 3 years until he started telling me, hey, there might be an opportunity for you. So I can't promise anything yet, but be prepared. And then sure enough, in 1999, he did ask if I could join the expedition. So you have to be a little patient. I think that's still true today. Some people waited shorter, some people waited longer times. It just depends on the kind of the team. It depends on the funding. Sometimes they can take 8 people. Sometimes they can take only 4 people. There have been times in the past where they've taken 12 and split into 2 teams. And so obviously if they take a larger team, there are more opportunities. And I think our year they had enough for 6 people, and then 2 people came for a shorter half season, for example. So that's kind of an intermediate example.
You were talking about the thawing cabinet, and one of our participants, I'll read the question word for word. How are nitrogen currents in the thawing chamber adjusted to prevent heterogeneous H2O's removal in large, irregularly shaped samples?
Yeah, that's a good question. I think that we probably, for these small samples, they will thaw out within a few hours, and that'll be totally fine. But we tend to typically keep them in there for a day minimum, just to ensure that they're totally thawed. Larger, as I mentioned, larger samples are kept in there longer. Sometimes we'll have elongate samples, or sometimes they'll just be like equidimensional shape. Really, the most of the moisture is going to be in the outer layers, or even just loose in the bag, like loose ice chips or snow that's in the bag that got collected. When the field teams collect samples, sometimes the conditions are very inhospitable. It's just blowing wind. Your fingers can be agile for maybe a minute, and you're trying to hold a bag and the little tag. You're trying to get everything together. So in the process, some snow and ice gets in the bag, and nobody worries about it. But then until it gets to us, then we have to worry about it. So we'll err on the side of caution and let samples thaw out longer if there's some question about its size or shape. And I think probably in the early years of the program, they did some careful thawing tests to establish some of these baseline times and sample size that we use now. When I became curator in 2002, the program had already been active for about 25 years. So there were a lot of well-established procedures.
You talked about these flow benches.
Yeah.
Out of curiosity, one of our participants asked, where does the term flow bench come from?
Okay, so these are these are the flow bench comes from, it's a good question, and it's one of those jargon things that we just kind of skip over and don't explain. But the flow bench environment is kind of you can see those filters in the back wall there. So the flow bench provides a very stable and gentle flow of air that doesn't cause disruption, but it creates a clean environment, keeps dust, if there's dust present, keeps it out of this area by creating a laminar flow across towards the person working in the flow bench. So it's a controlled environment. In that sense, it creates slightly cleaner conditions, and there are different kinds. You can get super clean flow benches, depending on the kind of filters that are used, and you can get less step up to less clean kind of flow benches as well. Again, based on the airflow and the filter type. So we like them in the meteorite lab because they allow more dexterity and flexibility, and they're used in a number of our curatorial activities around in the different collections because of that as well.
What advice do you have for these interns who may be thinking about pursuing a career in the sciences, a STEM-related career? What thoughts and advice do you have for them?
Yeah. Okay, that's a great question. I think that, and I've thought about this fairly regularly, I guess, as I step through my career. But my background has been in geology, and my degrees, my undergraduate and my graduate degrees were all in geology, which is great. I love geology. It's treated me well. It's my background has treated me well. But I think that I had a lot of additional training in the basic sciences, math and physics and chemistry. And I thought that was important early on as an undergraduate. And when I got into graduate school, it remained important. The faculty were all pushing, hey, you got to make sure you take basic sciences. And I realized at the time that a lot of my undergraduate majors had taken geology because it was more qualitative. It was you could take geology, it would be a science degree, but you could avoid the physics if you wanted to, or you could avoid the chemistry. So, and there's nothing wrong with that, but because I had a little bit of that myself. I think I was just more interested in natural science, and the rocks. Rocks were awesome, and they're still awesome. But there's so many aspects of geology today that rely on techniques, analytical techniques, characterization techniques, where you really make the biggest impact if you have a background in the basic sciences as well. So my advice would be to don't turn your back on the other sciences if you can, even if you can specialize or build up some expertise in one of them, whether it's math, physics, or chemistry. That will serve you well. It'll give you an extra sort of training that will set you apart. And mathematics especially, I mean, if you can combine chemistry and math, physics and math. Mathematics works its way into everything. And one of the things that I remember as a student was I loved math. I could do math pretty well, and I enjoyed it. And when I got into graduate school, it took a while for the obvious connection between math and geology. And by the time those connections were obvious, I hadn't had math for a couple of years, and it was too difficult to go back and relearn. I didn't, partly because of a time. You just don't have time to do that. So I realized, if these geology classes had incorporated math into the curriculum earlier, I could have made a smoother transition into some mathematical applications as well. And math, like I said, math connects geology and chemistry, geology and physics. And I think that if you can take math and do it, if you like math, do it, because there will be an application in geology if you want to combine those two. Those are, off the top of my head, those are my suggestions or recommendations. But one other thing that served me pretty well too was I switched. I hadn't planned on attending two different graduate schools, but I ended up attending two, Michigan and Berkeley. And looking back on that, it really was a great benefit because I met more people. I met more faculty. I met more students. And geology and planetary science, it's a pretty small community, but it's large enough that if you have those extra connections, that will also help you. There are a lot of, I know a lot of PhD recipients who they got their degree and they were only at one other school. When they're ready to graduate, they know fewer people, and you either have to work harder at making connections, which that's also fine, but if you know a few more people, it can help you too. So that's something that I didn't really realize at the time, but when I look back on how I've been able to find a career, that helped me as well, having that additional experience at a third school. So it's something to keep in mind as well.
And that's excellent advice, Kevin. And, to just add to that, to reinforce a couple of your points, that networking for you as interns with the folks you meet, the folks you interact with at conferences as part of your internships, make those connections, because those connections can help you in your future, as Kevin really stated there as well. And the other thing that I heard Kevin say was about, following your passions. He didn't say it in that sort of short, succinct word, but, between whether it's math or physics or chemistry or whatever your passion is, that can be such a helpful thing. Because if you love what you do, you'll want to stay in your job long term, and you'll enjoy all the work that goes along with it, no matter how busy you get. So thank you, Kevin, for those words of advice. Totally
agree.
Yeah. And it's about 18 minutes past the top of the hour, and I don't see any other questions in the chat, though I do see some Go Blues and hello from Berkeley's out there. So you got a couple of Michigan and Berkeley fans, as well as many other universities. So for all of you interns out there from LPI, USRA, Jacobs, NASA, Astro Materials, we look forward to connecting with you again in future meetings. And I want to thank Kevin and Suzanne for bringing us into the Meteorite Lab. And Kevin, especially want to thank you for sharing your expertise, your lab, your journey, and all the great work that goes on there within the Antarctic Meteorite Lab. So thank you so much, Kevin.
You're welcome. Thanks for having me on today. Bye-bye.